All right, we're just about to 5:15 Beijing time, so I think I'm going to go ahead and get us started. So welcome everyone to Right-Sizing Core Building Material Optimization. Let me advance the slide. There we go. In this session, we're going to be hearing about how to optimize structural elements in order to reduce embodied carbon. So my name is Lindsay Rasmussen. I'm a Senior Program Manager with Architecture 2030, and I'll be your moderator for this session. For those of you looking to get AIA Continuing Education credit, the learning objectives for this session are shown here. And we'll be following up with a survey after this on how to submit your information for AIA credit. We'll also be collecting all the questions submitted to the Q&A box throughout the session. So if we're not able to get to your questions, we'll make sure that we have our speakers answer that after the session, and then we can post that to the CarbonPositive website. Another note is we are recording all the sessions, and we'll also post links to the recorded sessions on the CarbonPositive website. So with that, it is my pleasure to introduce our two speakers for this session. I'll keep their introductions brief, so we have time for the content and for questions, but you can learn more about them on the CarbonPositive website. So to start, Robert Bamford is an associate at Web Structures located in Singapore. As an associate, Robert heads Web Structures' Future Design Studio, developing and promoting cutting-edge parametrics and advanced computational design techniques. Robert is joined by his colleague, Gaurav Gupta, an environmental consultant with WebEarth. Gaurav has been leading the efforts in the work on embodied carbon calculation and optimization within WebEarth. So with that, I'll go ahead and hand it over to you, Robert.
Okay, thank you, Lindsay. I hope you can hear. I'll just share my screen and hopefully we can make a start. Are you seeing is the presentation coming through?
Yep, that looks great.
Okay, fantastic. So thank you very much for inviting us to speak here. It's a great honor as part of this great sort of lecture series, and we hope to be able to show some interesting and hopefully useful work that we've been doing. The title of this is Right-Sizing Core Building Material Optimization. However, material optimization really is, we can think of as one of the, sorry, I'm having some troubles with my slides here. Okay, now we're going. Maybe a better title for this, or an alternative title for this, might actually be System Geometric Optimization, because really it's about geometry, that the sort of the research into the manipulation of geometry that can actually yield the material savings. So we'll be doing a lot of focus on geometry, but the actual purpose of this is to yield savings in material. And actually everything that we're looking at really is kind of a material, so it's not specifically steel or timber or concrete, but the strategies are geometric strategies, so they apply to all materials. So it's just worth bearing that in mind as we go through. Very quick intro to Web Structures. We've been based in Singapore for now more than 20 years and delivered sort of cutting edge design and sort of architecturally focused design office in Singapore. Sort of work that we've done has been sort of a very long and spread out resorts, as well as high rise, and again looking to sort of integrate structural systems within architecture as part of sort of holistic conceptual solutions. And sort of delivering also sort of long span structures for these for various clients across the Southeast Asian region and beyond, as well as the small and intricate. So we've always stayed sort of relatively keen to doing small bespoke work too. So these are sort of some of the projects that we've finished relatively recently, and very broad range of structures, all some varying levels of sort of sophistication and complexity, but all with a sort of an architectural focus and looking to really integrate structural systems within architecture as part of that overall design holistic. We'll cover a few of these projects in a little bit more detail in some of the case studies, but I hope that just gives a little bit of an overview of the approach of the office before we get going. As Lindsay mentioned, I lead our future design studio in Singapore. And so over the past 3 years, we've been looking at sort of how to develop new techniques to effectively find new ways to create structural efficiency through different parametric studies and optimization processes. So we're going to start really with quite a sort of maybe relatively simple structural engineering problem. Very typical. We will develop in complexity from here, of course, but this would be just to try and make an initial statement of this sort of right sizing. If we look at a very sort of typical beam spans and support conditions with a defined structural zone that is, say, 1.2 meters wide and 3 meters deep, the sort of more traditional, or the sort of maybe now we can say antiquated way of designing this beam would be to find the maximum bending moment and the maximum shear force, develop a section based on those two, and of course checking deflection and vibration, but then to provide that section over the entire span. So this would then give us, say, the right size. Except this, in terms of resolution and scale, this solution only applies at one specific point to the actual problem, at that position of maximum stress. So by looking in the detail, so increasing the resolution of the design, and now going into looking at 3 separate sections, 1 for each span, we now find we can tailor the section to each span and reduce the tonnage accordingly. Now we can keep doing these divisions. We're doing these divisions in factors of 3, and we keep finding that the weight keeps coming down. Effectively now each segment of the beam is being far better designed, and it's actually a much better representation of the material that is actually required to deliver the specific structural performance just locally in that area. We can keep doing this, and after a while we find when we start getting into sort of the very large sections that we reach this sort of point of diminishing returns where we can segment more and more, but we don't really get much extra benefit. So this is now segmented into sort of 729 sections, and we find this sort of this zone that we can't improve beyond about 340 kilonewtons. Now, this obviously introduces some fabrication problems, and there are various ways of dealing with these. But really, the key point here is just to get across that the closer you look into a problem and can design and detail it, then actually you can find substantial efficiencies by really applying just really commonly available software and techniques. So this leads us to our first first point, which is that by looking at the resolution of the problem is actually key to finding efficiency and material efficiency. Now this is of course just for a beam. Now if we were to look at the same solution space, so 3 meters deep, 1.2 meters wide, and looking at a relatively standard box truss here, again, now that we're using the sort of the geometric advantage here, that we're maximizing the depth of the structure, we can again find a material benefit here. And then by increasing resolution again further, by now going into sort of a space or micro framing solution where we can distribute material better and individually analyze each of these elements, we can again get substantial drops in material and improvements in efficiency. All of these, of course, have very, very real material benefits and of course sustainability benefits. So really, in terms of right sizing, it's a lot of these things are system dependent, but really the key is actually one of the key points here is about the availability of technology to fabricate things on a scale which they can be realized. Now the conventional materials and section sizes generally dwell up here, the top left, large sections and small numbers, and down here in this sort of small element size and large numbers is a sort of general limit of available to digital fabrication technology. And hopefully moving into the future where we can get into this microframing zone, we'll continue to be able to yield greater efficiencies and material savings. So along this sort of arrow, we find that there's increasing efficiency and innovation, and with investment and further research, hopefully the sort of the digital fabrication world will be able to sort of help to realize some of the capabilities that are already possible. You know, so in terms of a design perspective, we are able to realize these designs. It's a question of actually, can they be fabricated? So I'll move on now into topological optimization, which is now scaling up the element and looking at actually applying distribution of stiffness and material placement really across now larger elements as we're going to present. So this is an unwrapped elevation of a skyscraper as it happens, and we're looking to use these sort of topological methods to find efficient material density and what we call heat maps, so that we can then inform ourselves and then recreate framing using sort of strategies that can be built and can be realized. So of course, you know, this is how nature would build the building, but we have to sort of modularize given the current situation we have with technology. And so one of the strategies that we've developed here is to use a hexagonal grid to be able to move loads up and down, but also left and right. So you can see the hex grid stays in fidelity with the white areas where the material placement is shown to be, wants to be the highest, and then we have an infill weave. So this allows us to stay in fidelity with the findings of the heat map, but actually something that is buildable. We also carried out a case study on this super tall, super skinny resi in New York. So we recreated this building, which is a highly very sophisticated design, but obviously very portalized. Everything's orthogonal, and we recreated just the facade elements using using topology optimization, and reran the exact same structural analysis, same loads, same wind and everything, using this recreated facade frame structure. And what we found is that the building performance improved massively. So you can see the red numbers of the previous design and the black numbers of the new topological design. You can see that the lateral displacement reduces from 1.4 meters down to 800. There's a similar story for the building period as well. And overall as well, a 7.5% reduction in the structural mass. So it just goes to show that using these geometric methods, the geometric advantage really actually has it can not only achieve savings in mass, in structural mass and hence cost, but also helps to improve the overall building performance, in this case very drastically. This is another project that's relatively large, sort of 400 meter long, with large cantilevers. Here in Singapore, that we've again applied these methods to. In this instance, we've used topologies along the topology optimization along each facade. And then to recreate these idealized load paths, we used a sort of a diagrid intensification or patterning approach, as you can see here. So a primary diagrid, and then secondary, where the load lines are more intense, and then a tertiary infill where they're the most intense. So this strategy then allows us again to stay in good fidelity with the topology study, but to provide something that is repetitive and modular, or a complex modularity, as we like to call it. Moving then into geometric optimization. So the previous studies have had a predefined geometry or a geometric zone. This topic is now about manipulating the external geometry so that we can then look to find other efficiencies and improvements. So this is that same project as before, and here what we're doing is we're just manipulating the intersection positions of these bars. Small movements relative to the scale of the building to look to find overall efficiencies and reduction in the structural energy, or the energy of the mesh here. We find with these small movements and rotations actually can achieve a very large overall reduction in the energy of the structure, which then goes further to help to reduce is effectively how hard the structure needs to work. So this obviously yields reduction in material. This next study is a rivals pavilion in the Maldives, and this is a geometric optimization that is really we're just looking here to actually to find a geometry of the roof with 2 column support points. We're running this analysis simultaneously with the single objective of just minimizing the deflection. And so what this does is it creates a balanced structure where actually the overall deflection is minimized, but you're not creating points within the structure that are sort of are creating sort of overly weighing the rest of the solution. So it creates a very evenly deflecting and nicely balanced structural profile, which yields substantial benefits. This in fact compared to the original geometry, which is actually very similar to this. So we're not trying to change the overall architectural concept, but this is more than 30% less material than the original design. The same is true for this is an energy optimization for a transfer structure. And this is using a multi-stage geometric optimization approach. And the same scenario is true here, that these effectively we find that given the structural, the specific elements, the freedom to move around, we actually find that things very rarely want to be straight. They actually like to incline slightly. And so that when things are being analyzed under load combinations, including lateral loads, that actually it's very advantageous to have slight inclines that resolve globally, but can resist directly lateral loads through direct strut action. So, and this project here, 8 Conlay, is which would be the world's tallest twisted twin towers. Similar geometric optimization strategies were done as part of this global concept studies to get the overall framing of the structure. Here we're actually looking to maximize the rotation of the building as one of the objectives. So this is a multi-objective study, as well as giving the overall structure good genes to minimize the base moment and minimize the drift. So various of these things, can be studied simultaneously as well to give an overall a very good geometry, a starting point for a great geometry. And finally, just in terms of form finding, we've been doing some research with SUTD and Woha Architects into 3D printing in particular, and developing these neurological structural methods, sort of in the microframing world, where we can create very complex but sort of multi-noded arrangements, geometric arrangements, which we can layer optimization techniques on. So here's a further geometric optimization technique on top of that to minimize the energy of the structure, to create these super efficient structures that effectively, could depending on the scale of what you're looking to replace, could have huge savings over say just solid concrete columns or etc. So we're doing some work in this sort of realm at the moment. Each of these segments has been analyzed through ETABS, and so this is the direct size output from there, which we can then post-process to create our printing mesh. And then furthermore, then this then becomes the 3D printing path coming up through the structure. And you can see the underlying very regular cylindrical geometry of each of these elements, but as a whole, super complex geometry to realize. Just slightly conscious of time, so I'm just going to fire through here. And so effectively what we found is that, when we're looking at these, when structures are given the freedom to actually find form, that they rarely want to be straight or horizontal, and actually it's looking into these interstitial zones where columns can branch, and where horizontal structures can can come in at diagonals, where effectively a beam can become a column, and a column can become a beam, and this is where there's very substantial structural benefit to be made. So I think looking at structures and buildings and from a geometric perspective, I think we really need to, what we found is that actually looking back to nature, we found that we started to the efficiency comes in these in actually very natural shapes, and going through this process, which has actually no drivers that we're not forcing this to look like trees at all. It's just that it happens to be going in the same direction that nature has obviously been going in and realized and known for a very long time. So with that, I will pass over to Gaurav to continue. Thank you, Gaurav.
Thanks, Gaurav. Let me first share my screen. Okay. Hope my screen is sharing now. And hi all, my name is Gaurav, and I'm glad to be here to discuss about the big issues that we are facing, carbon emissions, and what in web structures, what we're doing about it. So I will pick up where Rob left. The second part of this presentation is actually demonstrates the process of assessing the design options on the environmental parameters. We do this using a tool that we developed in-house. It's called Epsom, which quantify and optimize the embodied carbon in the projects. This tool can be used from early stages of design, such as concept design, to the detailed design of the project. Before moving in the details of what the tool does and the interface, maybe it's important to understand the design thinking behind the tool. And for that, we divide the building into some key components. Maybe it's like a dissection of the building into key components, which are substructure, superstructure, finishes, services, and others. These key components can further be categorized into smaller categories, which is are the components of the building, such as substructure, facade, internal walls, so on and so forth. And finally, these categories are made up of materials, the real materials like concrete, recycled, steel, aluminum, and so forth. And all these materials have embodied carbon in them due to their extraction and the manufacturing process. Naturally, all these elements, all these materials have a different impact on environment. Some are harmful, some are more harmful than the others. So to test that, we calculated the embodied carbon of on one of our project, reinforced concrete building, and we found that most of the carbon, about more than 70% of the carbon, is coming from concrete and steel, and that was quite alarming. So for the first version of this tool that we are developing, we are focusing on the key structural materials because those are the ones who are contributing most in the embodied carbon. Just to summarize, out of the categories that I showed before, we are looking at two major categories: substructures and superstructure. Five structural categories: columns, frames, walls, floors, and stairs, and 7 structural materials. And all that consolidated comes into this tool called Epsom. It is an automated design tool that calculates embodied carbon with one click of the button. One click of the button is something important. I will explain it in the coming slides. And just to before we go to the interface of the tool, just to check that it might look like, or is it's some carbon accounting tool, or is it quantifying carbon? The answer is no. It's a design tool. And the way it is designed, it can be used from concept to the design development stage. I'll just take an example that in a conceptual stage, when we have structurally optimized options, which are through parametric approach or a conventional approach, they can be processed in Epsom in the workflow, and we can Epsom can process and produce fewer options that are more optimized than the original 5 options. And when the design is more resolved and more detailed in the schematic design, we can repeat the process and process the options from through Epsom, and potentially we get finally the best optimized design, or maybe 1 or 2 design options that are the best optimized. So the idea behind, the intent behind this tool is to enable designers and users and the stakeholders to take decisions which are environmentally informed in the design process. So at any time that you want to check your design, you have a tool available to check the performance, environmental performance of your tool or design. So now I'm moving to the user interface. So Epsom currently the way it is designed is it's like an application that can be installed and it finds its space in the Revit environment. This is how it looks. So you can go to the add-ins. Once you install it, it will be in the add-ins in the Revit environment. And once at any point of time the designer wants to check the environmental performance, they just need to click on this button. Once you click on this button, there will be a dialog box that will pop up. It will take 5 to 10 seconds because Epsom will be processing and calculating the results. And by the time this dialog box opens, you already have your embodied carbon calculated, and the result will be shown in a better visualized manner. I will just go through some of these tabs that you can see in this dialog box. So the first tab is about the project information tab, which take the usual information, the location of the project, and etc. etc. The two key information that we need to put in is the GFA and the CFA of the building, gross floor area and the constructed floor area. That will be used to calculate the embodied carbon index as well as the COI for the project. Finally, when you go to the material, so the next tab is the material tab. Epsom represent the embodied carbon in material and category tab format. What that means is in the material tab in the top image, you can see that there are 7 identified material that we showed in the design thinking process, and there are 5 structural categories that are being identified. So for each material, you can see at the bottom left corner the total embodied carbon, and you can also see the breakdown of embodied carbon by each category. Similarly, the category tab is a pivot of the material tab in which you see overall categories, the 5 categories, and the breakdown of embodied carbon in material wise. And the bottom left, you can check, you can see the embodied carbon per category. So what it does, what is the benefit of this? So the benefit is at any point of time, the user would know where the carbon is going, and where you need to optimize the carbon, being it material or being it a category. The next tab is the settings tabs. Although the way it is designed, the Epsom can produce result as soon as you click the button. However, that is on the concept design. As soon as you go to the detailed design stage, you are able to have more information about your project and materials. So Epsom allows you to change certain parameters such as carbon factor, density of the materials, subgrade of the materials. So the idea is the more information you have, the more refined number you'll get. And finally, the visualization tab. That's the most useful tab to represent data and to strategize your approach towards reducing the carbon. The data is shown in 2 bar chart and pie chart, which are the commonly used graphs, and they are material wise and category wise. So these 2 charts are very helpful to check on which component of which material is taking a lot of the carbon. At the same time, on the right-hand side of on the dialog box, the Epsom calculates the embodied carbon index and COI automatically, as well as it gives you the environmental impact of your design in forms of trees, acres of forest, carbon sequestered by acres of forest, and car emission per fuel. What that does is it allows the user to have an imaginable scale of the environmental impact. Some user might not know what is the meaning of 8,471 tons of carbon, but they would know that it is equivalent to 1,660 car emission per year. So that is something imaginable scale, and they can work on their design to reduce the embodied carbon of the project. Last, all this data can be easily transported into the Excel files by just click of the Save Excel buttons, and then you can use this data for further data analysis. With that, I will hand over to Rob to just wrap up the whole presentation. Rob, over to you.
Okay, thank you. Okay, I hope you can all see my screen again. So I think that effectively what myself and Gaurav, although from slightly different disciplines, but the intention is that we're on maybe different sides of the same coin. that we're looking at sort of, you know, natural, but trying to be responsive to and inspired by, but also responsible for the natural environment. I think in terms of a comparison of where we need to be thinking and where we are, the natural environment, you know, has got no straight lines, no right angles, and has evolved in this way, using branching techniques, and creates very, very efficient sort of natural structures. Whereas the built environment, conversely, everything is a right angle. Is either vertical or horizontal, and there has to be this happy medium in between where we can start to use and apply some of the rules of nature to find these efficiencies that we've been showcasing, that can be found from the geometric advantage and geometric optimization, and effectively giving structural elements the freedom to find the most efficient arrangements. But also to sort of respond, you know, so that we are sort of more aware of the environment in which we're trying to design. The other thing is I think we need to be aware of what we're trying to target, and I think innovation in this field is very important, and that many solutions will come out of innovation. One of the sort of aspects of this is that there may be better material savings or potential, but more material savings to be found in innovative approaches that have yet to be developed, rather than trying to focus on the sort of the top left-hand corner of our previous chart in the conventional solution space, which has, you know, will only yield diminishing returns. I think these are some of these, you know, as these sort of 16 captions come up, these are some of the tools and maybe some of the techniques that will sort of allow some of these solutions to be propagated from. And so on that note, we would like to take any questions.
Great, thank you so much, both of you. That was an incredibly fascinating presentation, and really beautiful graphics as well. If you have questions, please go ahead and enter them into the Q&A window. I have a couple I can go ahead and start with, though. So thank you for sharing the tool, Ipsum, that you've been using in-house. Robert, for the parametric design side, it looked like Grasshopper, but what tools exactly are you using in that regard?
Yeah, we use the sort of Rhino Grasshopper with, you know, a lot of different plugins, most of which are freely available, some of which we sort of we then sort of create ourselves to do specific tasks. But it's Rhino Grasshopper environment for all of this geometric optimization stuff.
Great. Thanks. I'm wondering if you have advice for people that are either entering the world of parametric design or are not as familiar with parametric design, on how to reach some similar results in terms of structural optimization for embodied carbon reduction. Yeah,
so my role is not is more. I'm not say a hands-on user, although I can navigate fairly well. So there's two sides of it. You need the very capable colleagues who can create the scripts and realize the sort of the intent. And on the other hand, there's also trying to actually understand what you're trying to get. Make sure to set the right problem. And then to be able to assess it through conventional means, or to understand what answer you're trying to get. I think that's probably the same as with any sort of modeling technique. But you have to, obviously, you could present the solution, that you've got to know where the right solution space is, and what you're trying to get out of it. It takes a team, though. It really does. It takes a team working together. And in our team, there's myself as a structural engineer, and then we have mainly then architects. We have another engineer as well, who's also a sort of very, very advanced mathematician. And we have coders and architects, and so for 3D graphics and understanding and rendering and these things. So it takes a bit of a combined team is what we found works.
Yeah, absolutely. I gather that from the relationship just between you two. So from the parametric background to the environmental consulting and architecture background. But I think that's an incredibly important point, that it takes a lot of collaboration, especially early in the design process, to have significant embodied carbon reductions. Following up on the tool thread, so Ipsum, it's a plugin for Revit. Is that, it looks like it's not proprietary. That's something that people can find and install on their own, or how do they access that?
Right now we have been using this in-house because we are making an inventory of multiple projects. We intend to test a lot of projects to be able to modify the tool more. At the current moment, we can estimate stage 1, A1 to A4, meaning until transport emissions, we can estimate through Ipsum. But yeah, we do intend to launch it in the market for people to use it, and so that even when they're using the software, they can input back in terms of what are the results, and of course what are the drawbacks. So yeah, as of now, we are using within our company, and that's about it.
Great. Are there any other tools you typically rely on, or resources that are your go-to for embodied carbon reduction?
For now, since we're developing this, and it has been developed for quite some at quite some stage, so we are using Ipsum. But yes, we are looking at tools like one-click LCA, and there are a couple of other tools out there in the market. So we do have an eye on them, so that we also develop something that is an addition to the industry. Yeah.
Great, thank you. Let's see, I think I have one more question. And again, to our attendees, if you have any questions, go ahead and throw it in that chat window or the Q&A window. But one question we get asked a lot in this realm, or along this topic, is the balance between upfront embodied carbon savings versus longevity of a building. So designing for a longer lifespan. Of course, your approach with material optimization is reducing embodied carbon upfront. But another component of this conversation is material substitution. So like mass timber products versus concrete and steel. Do you want to maybe talk more about that in some regard?
Yeah, I mean, this is really just one aspect of an overall strategy to reduce and minimize carbon. Of course, if timber solutions are available, then we know that the material choice is going to be hugely significant in doing that as an overall point of view. But the design strategies still apply. It's a material thing. The geometry doesn't know what the material is when we're doing the geometric optimization. But the material choice, also the transportation of the material, and then these sorts of strategies and specification and design for disassembly, and the whole thing is part of it. So this is only one aspect. So of course, I mean, I always advocate for frame structures over shear wall structures, and for reasonably high live loads to allow for flexibility. And I think we have a lot to learn from looking at successful building stock in the world, and also less successful building stock that gets built by developers to be flipped and becomes disused in a very short period of time. And because it was built with, say, a shear wall system, that it doesn't have inherent flexibility, and becomes disused, and so is ripped down, and it can't adjust to market trends. Whereas sort of 1920s, 1930s New York or sort of Manhattan real estate, which high ceilings because they needed to to encourage light at the time, designed for high floor loads because they had a lot of machinery at the time. It just happened that this building stock was is very, very desirable today because you can fit in you can put underfloor heating or radiant floors in as you wish. It has that extra allowance. You can reconfigure the partitions and re-subdivide because it's a frame structure. So I think, this is something that, definitely is worth advocating for. The other point is maybe loosely on the same topic is that good clients are probably the ones that are the most likely to take on sustainability or have sustainability objectives. And so we call these good clients, of course, because they're sustainable, but they also were the ones that would maybe invest in their own building the most because they want to occupy it for a long time. So this might be a university or someone like that, but they're going to occupy their building. They want to invest and be proud of it and have the sustainability credentials. So they're doing both aspects. They're not just using sustainability techniques, but they're actually occupying the building for a very, very long time, which means that, it gets good use. Whereas the other end of the spectrum, the developers say, the bad developers, where cost and turnover is maybe the main objective. They're less likely to use sustainability or sustainable methods, and the building is less likely to be used for a long time, more likely to be demolished quickly. So you get both ends of the problem with those types of buildings.
Maybe I like to add to this, if I may, actually it's a very good question about upfront carbon and the longevity of the building. These are so. In my opinion, the upfront carbon is for a building. Definitely, that's something that we are working on to reduce by various tools. But the longevity of the building is another way to reduce the embodied carbon. What I mean by that is, like for example, in Singapore, the life of a building is 50 years, and in 50 years, even if the building is in good condition and you're going to demolish it, that means you're going to, first of all, you're using the embodied carbon to demolish it, you're using energy, and at the same time, you're going to construct a new building. But at the same time, if you can design your building to be flexible enough and resilient enough to be able to accommodate the uses and the changes in the uses over the span of, say, 100 years, that you're almost saving 50 years of embodied carbon, meaning maybe the upfront carbon is just the capital cost or the capital carbon that you're putting in, but the overall return of investment might be the approach of longevity of the building and flexibility of the building might be a good approach to reduce the embodied carbon. And that's where the concept of circular economy, where you are trying to waste less and reuse what you have. So rather than taking something from the environment and dumping it, use the same thing again and again until the time it's kind of serves its purpose.
Absolutely, yeah. I think that really incredible insight, and I think that's a perfect point to end on as well. So thank you both, Robert and Gaurav. A really incredible presentation, really great expertise and insight. Thank you both for your presentations, and to our attendees, thank you as well. We have our final session of the day right after this, so we look forward to seeing you in our final session. And with that, thank you.
Thank you.
Thank you very much.
Bye-bye.